to be chairing the first session, which is about bandits. We have 5 talks. There's one announcement about that, so if you're giving a talk, then you should be giving those people in the back, you should be giving your presentation to those people over there on a USB stick or something. And that's how it goes. But I think we got several speakers. We got 5 talks here. The first one is given by Kwan, so let's hope that you can find his presentation.
Thank you. Hi, I'm Kwan. So happy to be here. So I'll talk about our work on obtaining data-dependent bound with T-optimal best of both world guarantees for multi-arm bandits using stability penalty matching. This is joint work with Shinji Ito, Junpei Komiyama, and Nishan Mehta. So let's start with the setting. We consider the classic multi-arm bandit setting with K arms, T rounds, and losses. Psi losses are in the range -1 and 1. We study the regret of the learner with respect to a single best arm over T rounds. We assume that the losses are sparse, meaning that there exists a constant S such that in every round there are at most S arms with non-zero losses. And the goal is to construct regret bounds that will hero with S instead of K. So for adversarial bandits, existing work have established a lower bound of order square root of S times T and near matching upper bound of order square root S times T log K. For stochastic bandit, we also have a lower bound of order S log T over the delta mean. So here, the delta mean is the gap in the expected loss between the best and the second best arm. That's also been best of both world bounds with a suboptimal dependency on T with an additional log T factors in both settings. So in our work, we answer two fundamental questions. The first one posed by Kwon and Purchase 2016, which asks, in adversarial bandits, is it possible to obtain an upper bound of order square root of ST log K over S for psi losses when S is known? We show that the answer is yes, and not only that, but the bound can be obtained in a best of both world fashion. The second question is it possible to achieve bounds that are simultaneously best of both worlds, T optimal and S agnostics? And we also show that the answer is yes by showing a best of both world bound, which is a log K factor more than the two lower bounds. Our bounds are proved using the follow the regularized leader framework. So essentially, we're running FTRL on the sequence of unbiased loss estimates. And the regularizer function is phi. And in every round T, we use a time varying learning rate beta T. So the regret bound of FTRLs can be seen as a sum of two terms, a penalty term and a stability term. So the penalty term is HB beta T plus 1 minus beta T times HT, and the stability term is DT over beta T. So HT is not important for the talk, so we'll instead focus on ZT. So ZT is a function of the loss estimate vector in round T, LT hat, PT, and PT plus 1. So the main question is how do we tune the learning rates, and for that we use a method called stability penalty matching or SPM. And the main idea of SPM is that the learning rates are set so that in expectation, in every round, the order of the two terms are the same. SPM was first introduced in a Code 2024 paper, where it was said like beta T plus 1 minus beta T times HT is equal to an upper bound on the expectation of ZT over beta t. And in this work, we use a new variant of SPM that we call the real-time SPM. And the idea of real-time SPM is that we're gonna use ZT instead of the expectation. So one example with the alpha the stylus entropy is that in our work in the update rule, we use mean of PTIT 1 minus PTIT raised to 2 minus alpha times LTIT over PTIT square, which is different from SPM, which uses so summing from k arm of I from 1 to k, mean of PTI 1 minus PTI raised to 1 minus alpha. And so let's compare the two. So we can see that the expectation of ZT is bounded and easier to control. However, its exact value would require knowing the losses of all the arms. So that means that when we compute an expectation, an upper bound on the expectation, we have to take the absolute, we have to assign value of 1 to the absolute value of all the non-observed losses. On the other hand, for ZT and its upper bound, it can be unbounded whenever PTIT is small. However, they are fully observable because they only require on the observed loss LTIT. And so that is important in making the bound eventually become adaptive to S. So next is the analysis of real-time SPM. We have a theorem showing that the regret bound of real-time SPM can be like it's a sum of two terms, a best of both world term and a leftover term. So in the best of both world term, the green quantity over here, that's the mean of two square roots. So the first one corresponds to a bound in stochastic bandits, which is of order log t times the expectation of ht/zt summing over t rounds. And the bound for adversarial bandit is expectation of max ht times the sum of zt. And then the leftover term. So we look at the best of both worlds term first. And the main question is, how do we make so the main question on the benefit of this term is how does that lead to an sparsity dependent bound? And the short answer is that both of the expectation HT, ZT, and ZT will depend only on the arms with non-zero losses. For example, if we take an expectation on the upper bound of ZT, then we can show that eventually that will only depend on the losses of the non-zero arms, and then that so that can be upper bounded by s raised to alpha. And then next we bound the leftover term. So the leftover term is of the form expectation of max of zt beta t times the log of the sum of zt over ht. And so it would be great if two conditions are true. The first one is that the max term is polylog t at most. And the second one is the expectation of the sum inside the log is polynomial in t. If the two conditions are true, then that will make the leftover term is of order polylog t at most. So we don't have to care about it. And the main question is it possible to make both 1 and 2 due to hold and how? So fortunately, the answer is yes. To make the first condition to hold, we can add the log barrier function into phi t. So the regularizer in each round will be equal to beta t times the alpha the stylus entropy plus gamma, which is a constant, times the log barrier function. And to get the second condition, it turns out that we can simply mix 1 over t into the sampling probability vector. So this ensures that PTI will be lower bounded by 1 over t for all round t and arm I. Wait. Okay. So putting everything together, we obtain a best of both world bound for bandits with sparse and side losses. These bounds depends on alpha, and the idea is that we can tune alpha for both cases when S is known and unknown. And so by tuning alpha, which is setting alpha sufficiently close to 1 but not exactly 1, we obtain a best of both world with optimal dependency on both S and T for both cases when S is known and unknown. And when then S is known, so we can also to alpha as a function of K and S. The final remark is that real-time SPM can be adaptive not just to the sparsity of the loss sequences, but also to the unknown variances as well as the total loss of the best arm. Thank you. So for the so when S is unknown, then we can obtain a log K factor more than the lower bounds. But when S is known, we can improve the log factor from K to K over S. So for unknown S, first of all, we run FDRL with alpha the Silas entropy, and we obtain the bound over there. And then just tune alpha after that. Yeah.
So any other questions?
Yes.
Is there a difference if the losses are non-negative or non-positive? Can you get special bounds in these cases?
Yeah, so these results hold for losses in the range -1 to 1. So we only need that the losses are bounded, but it doesn't matter. Yeah, so in the 2016 paper, there's a difference on the kind of, like for the proof of the lower bound for one of the cases is more involved, and then the upper bound can also be better. But I think it's, yeah, so in this work, we kind of reconcile that. We say that, okay, for negative and positive losses is the same. We just apply this one and it works, yeah.
Anybody else? So I'm also just wondering, like, do you think that all of these tricks, like this additional log barrier into the regularization, is this like necessary to solve this problem, or is it just what you managed to do?
So I think the log barrier was introduced to bound the leftover term, and it is conceivable that there might be a different analysis that either get rid of the leftover term or just doesn't need to like make bound it in a different way. So yeah, it's possible. Yeah.
Okay, great. Thank you.
Thank you.
No, I think. All right. Okay. So maybe just another announcement for those of you that missed the initial announcements. So if you're giving a talk, then please pass your slides to the people in the back on a USB sticks.
Hello, hello. Can you hear me?
Right. Yes. So the next talk is given by Diraj. Is that right?
Yes.
Okay. Yeah.
Okay.
All right. There we go.
Right. Let's see. Does this work?
I think we're gonna keep.
Okay. Right. Hello. I'm Dheeraj Narasimha. I'm going to present my joint work with Nicola. It's on the use of model predictive control to almost solve restless multi-arm bandit problems. We are from the University of Grenoble, the INRIA at the University of Grenoble. So let's begin. So our bandits are slightly different from the bandits in the other talks. Our bandits have states which you can observe, and you can choose actions, 0 or 1, which is typical, and you can observe the rewards for these problems. In this case, we have n bandits, which are known. And the thing about these bandits are that they're Markovian. And by Markovian, what I mean is that when you choose the 0 action, there's a certain transition kernel, and when you choose the 1 action, there's a different transition kernel, right? And we have a slight twist, which is that there's a constraint on the number of arms you can pull at each moment in time. So for example, if we've decided that you can only pull half the arms, then basically that means that you can only pull the last 2 arms, for example, or only 2 of these arms out of 4, right? So given this, a typical example of this is the problem of sending packets in any cellular transmission, where you have limited bandwidth and you need to send out, let's say, 5 packets, but you have 10 devices connected to a tower, right? And the problem formulation we're looking for is essentially the average reward formulation. So what we're trying to do is maximize the reward over time, average reward over time, where we're averaging over all n arms, and we're making sure that each of these arms obey these Markovian transitions, and but at each instance in time, you need to satisfy the constraint on how many arms you can pull. So our coupling occurs entirely through the action space in this case. Now, obviously, we're not the first people to look at this problem. The first person to formulate this problem was Whittle back in 1988. And what he suggested was, let's not deal with the complicated problem of coupling the actions at each time instance, and let's try to average over all the time. So basically, on average, I need to satisfy the time, the action constraint, but not necessarily at each moment. Right. Now, you can show that this version of the problem is equivalent to a fixed point problem, where y is essentially the state action frequency. And this is the fixed point that y needs to satisfy is essentially the stationary measure of the state actions. And what you want to show in this case is that on average, the state action frequency is less than or equal to alpha. So here's a brief timeline of how things have progressed over the years. So back in 1988, Whittle came up with this problem, and he said that under a condition called indexability, his relaxed problem should be optimal. This was his conjecture. Now, in 1990, Weber and Weiss showed that this isn't quite true, right? That they came up with counterexamples for this. But they said that under indexability and a really hard to verify condition called U-gap, you can actually get asymptotic optimality using Whittle's index policy. Cut to 2016, and Verloop said, well, indexability is a little too much to ask for, but even if I get something called, I can use an LP index to do this, which is a slightly expanded version of indexability. I can still create a priority policy that will solve this problem under the U-gap assumption asymptotically. So in the meantime, a whole lot of work has been done, right? And one of the major things that people noticed is that this really hard combinatorial problem of trying to optimize over n arms, while asymptotically it's supposed to be optimal, in performance it does really, really well, right? It's not just that it's asymptotically good, it's very good in practice. U-gap be damned, right? And this sort of leads us to this result in 2021 by Yan, Gast, and Gojal. Gojal and Gast are both in the audience, by the way, which said that if U-gap is satisfied, you have this very surprising convergence rate, which is actually exponential in the number of arms, which means that you can actually, this sort of explains why Whittle's index is actually that good at solving your problem. And along the same lines, they said, well, the LP priority policy under the U-gap condition is also exponentially close, and that sort of loosened the indexability condition. So what you're seeing here is people saying, okay, initially I need this thing called indexability, I need U-gap, and if I have both of them, I have something that's asymptotically optimal. What you slowly see is, okay, you don't need indexability, and you'll still get something that's asymptotically optimal. And now we say, well, no, you don't need indexability, and actually you get exponentially close to the best solution. Now, in 2023, there was a paper by Hong et al. That showed that you can actually loosen the U-gap assumption completely. you can replace it with a much more easy to verify synchronization assumption. And under that, you get a 1 over root n convergence rate, right? And the same people said, well, if you do a little more, you can actually sharpen this up to an exponential rate. But their assumptions to us still look a little hard to verify. And that's why you come to us, right? So we're claiming that you can actually get the exponential rates under a much, much easier assumption to verify called the ergodicity assumption. And that is sort of what brings us to the talk we have today. All right. And another thing that we kind of noticed was that while the policy that Hong et al. Suggested is asymptotically great, in practice, it kind of lags behind. If you take a random example of a restless multi-arm bandit instance, it doesn't perform all that well in practice, right? Because typically most arms do satisfy some variant of UGAP, so it tends to lag behind a little. And even the simple priority policy actually does tend to do really well in those sort of cases, at least initially. And our own policies sort of do better, but that's what you expect in a talk like this. Okay. All right, so now what exactly is our version of solving this problem? All right, so we say, okay, let's go, instead of solving the full infinite horizon problem, let's solve a finite horizon problem with a finite horizon tau, right? And we now have a sort of Markovian constraint here, but this is actually this is a slightly simpler problem because it's all deterministic, right? We're not dealing with a stochastic program now. We've decided to sort of solve it using a deterministic problem of horizon tau. And what we say is, okay, when you solve this LP problem, you're going to get tau solutions from it. Pick the first solution, find a way to round it back to something that can actually be used, plug that in to your bandits, and then progress one more step, and then do this again, right? Fairly easy to implement. And we call the average reward that you get from doing this policy LP tau, right? This is our policy. And the next thing that I want to talk about is the assumption. So our assumption is that if you freeze one of the arms so that it always plays 0 and the other arm to play any action A, then after k steps, we want to make sure that two bandits that start at arbitrary states will eventually synchronize. This is our ergodicity assumption. And what we can show is that under this condition, you get an error of this form. There's a sort of small error that comes from choosing a finite horizon, a rounding error, which comes from taking a deterministic solution and using it for a stochastic problem, and an additional concentration of measure result because you're taking a stochastic problem and turning it into a deterministic problem, right? And so I'm going to skip over a lot of the proof details, and there are two major portions to our proof. One is dissipativity, the other is concentration of measure. Concentration of measure is more standard, dissipativity is less standard. So that's what I'm going to talk about, but I'm going to treat it as like an algebraic thing. There is a lot more to it than that, but no time. So what we're going to, so from the original fixed point problem, what you can obtain is the best solution. What you can obtain is a Lagrange multiplier for the fixed point constraint. If you use this, you can actually rewrite the cost problem as a rotated cost problem and notice that every cost that you get is non-zero. And what we can show is that there's an equivalence between the LP problem and a cost problem. And he's telling me to rush, and so you can use this to show that it's actually good enough. And we have a bunch of open problems that are related. One is, do we really need the almost? My contention is no. Is there a good way to optimize the horizon? I say yes. And is there a better terminal condition? I don't know. All right, thank you.
Thank you. Any questions? So if I understand correctly, then your algorithm is based on computing a solution to this LP,
Yes.
but that only gives like sort of like an occupancy distribution, and you still need to extract a policy from that.
Yes.
So,
Yes.
so can you say something about how you do that?
So this is called randomized rounding.
Uh-huh.
And what you do is once you get the Ys, you basically, you can actually come up with a way of picking zeros and ones so that your marginals satisfy the original set of Ys. So basically, and that gives you a sequence that will, with very high probability, give you what you want. Right.
Yeah, cool.
Yeah.
Still looking for questions?
Yeah.
Do you need to solve the full LP at every step, or can you do it in an online fashion and only one iteration?
We haven't tried to optimize how to solve the LP perfectly. So for us, we came and said, okay, go tau steps, solve it. And our tau was like 10 or 5. It's very small. And that sort of worked itself out. There's a reason for that, but time. If you want, we can have a discussion after the, yeah.
Okay, thank you very much.
Thank
you. All right, I'm still trying to identify the speaker that comes after Kwang. So if you're here, is it you, Eddie? Okay. So then please pass your talk. Okay, perfect. Then you're all set. Okay, so next up, we got Kwang, who I think is talking about offline bandits.
Yes.
As soon as the slides show up.
Okay.
Right, amazing.
Let me test if this works. The controller is not working. Okay, meanwhile, my name is Kwang Sung-jun. I'm at the University of Arizona. This is joint work with Jong-ha Ryu at MIT, Jung-Hyun Kwon at UW Madison, and Benjamin Kopp, who was at University of Arizona and then transferred to Cornell. He's an undergraduate student. It's not working. Yeah. Okay. Yeah, I think it works. Okay, so offline contextual bandits, very simple problem setup. There's a data collection procedure that we don't have control. It's an iterative process. You observe a context IID. It's called XT. You take an action following a behavior policy, so that's a randomized policy. And you observe a reward that's about that action you have taken and the context XT. And that's in 0-1 interval. And now after then, you have a bunch of triplets, XAR, and you have a policy class among which you want to choose the best policy. So what policy you want to choose? You want the one that maximizes the expected reward. And we're going to call that expected reward the value of the policy pi. Okay, no realizability assumption here. Very simple. Now, what kind of guarantees you want? Because it's not realizable setting, you just want to bound the difference between pi star and pi hat. Pi hat is the one that's returned by the algorithm, right? And those algorithms that do have guarantee on this, they will all follow that kind of order. So you can see that there's a square root 1/n, very familiar term. But there's a factor that's dependent on the both behavior policy and the best policy pi star. And that will typically rely on that R tilde, which is basically inverse propensity score estimator. That is a random variable because X is random. Now, we have two different problem setup. One is off policy selection, which is assuming finite cardinality of the class. So imagine that you have a bunch of policies already trained from whatever method you have used. You're now just trying to enumerate them and use holdout set to find out what's the best among those handful of them. So this reduces the burden of optimization because you can enumerate for each, you compute something and then select the best. Off-policy learning setting is the case where the policy class is potentially infinite cardinality. So here, you typically want some oracle efficiency because otherwise you can't implement it. So for selection, which is basically model selection in this task, we achieve, for that blue box, we're gonna have square root of the variance of that random variable tilde r star. And that's an improvement from the previous state-of-the-art Saki et al., which has second moment, right? The difference is first, variance is better than the second moment. And next, square root of the variance is typically less than or equal to the variance. And typically these are a value that's larger than 1, so this is a better quantity. For off-class policy learning, where you have the restriction of having to be oracle efficient, we developed a family of algorithms that satisfy certain condition, and it'll match the Saki et al.'s rate. So that's a theoretical development, and how did we achieve that? The way we do it is, of course, pessimism. So I try to explain it a little bit. Typically, you would form an unbiased estimator inverse propensity score, and then for each pi, you compute that, and then you choose the one that maximizes that. Or you could do pessimism, which basically computes a lower confidence bound on the true value of that policy. And the effect is that each policy, depending on how it assigns probability to actions, it may have a very large variance in the estimation. And if so, you want to kind of give penalties for that because it will mess up the whole process. And I will not give too much details on this plot, but basically pessimism is the standard, and how we improve the bound is just to come up with a better confidence bound. Okay, so previously I told you that we typically use that inverse propensity score, and you can compute that estimator for each sample, the triplet X, A, and R, and that will be a random variable that can be potentially unbounded. So as long as you can develop a confidence bound for this non-negative but unbounded random variables, then you can solve this problem. So now let's focus on that LCB for this unbounded random variables. A naive attempt you could be doing to obtain a tight bound is something like empirical Bernstein, where you just estimate the empirical variance directly. But first of all, the proof doesn't work, but you could say that maybe you don't know how to prove it. Maybe it's still a pretty good method. But keep in mind that you're estimating the variance. Then if there's no force moment, then that may not converge. It might keep oscillating even if the sample size n goes to infinity. Okay, so what we proposed is pessimism by betting on semi-unbounded coin. And basically, I will not give you much details, but there's a magic score function, and it's a non-increasing function of the mean nu here. And then there's some magic threshold. You find the crossing point. That becomes a lower confidence bound. And we prove that that's a valid lower confidence bound. This V hat is the one that crosses that point. So this second inequality says it's a valid lower confidence bound. But then the first inequality is explaining that it will not be too far away from the true value. And how close it is, it can be upper bounded by square root of the variance of that R tilde star over n. So that's how our improvement came. Right? So once you prove this, then there's like 3 or 4 lines proof for completing the ultimate statement for contextual bandit problem. Right? This is just for the confidence bound. But this is where most of the effort has been spent. And just to give you some connection, this is motivated from variation of some coin betting game that has been very useful for constructing tight confidence intervals for 0-1 interval bounded random variables. But we extended it to unbounded case. And indeed, when you do some experiments with random variables that has infinite fourth moment, you can see that our method PUB shows a very stable growth over the sample size. Whereas if you use empirical Bernstein, you can see a lot of this sudden change. You can see this confidence band also like changing dramatically at some point, even if it's averaged over 100 times, because that will not concentrate that variance estimate. And this is one example individual run, right? You can see this unstable behavior of empirical Bernstein. Okay, and we can do some model selection task in contextual bandits. And we just took the repo from previous work, Wang et al. From 2023, and just ran their code. Ours, so there are 3 different data sets with different, 3 different sizes. For small size, like using 1% of the total data, typically we outperform both previous state-of-the-art and the empirical Bernstein. But it's overall never worse than other existing methods. Okay, so conclusion, it reduces to 0 infinity value random variables. We improve confidence bound. It improves the performance of the contextual bandits. There's a policy learning part that I didn't get to explain, but I'm happy to explain to you if you come talk to me. And so yeah, feel free to grab me and ask any questions. You can email. We can schedule some time to talk about this. So that's it. Thank you.
All right, any questions for Kwang?
Hi, thanks for the talk. One question, you had a variance term for the off policy selection, but not for the learning case. Why?
Right, yeah, so it's just that, okay, I didn't prepare it, but you can, if you don't require oracle efficiency, then you can actually obtain the same bound, but that will not be oracle efficient. It will be like mean max 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 problem, and you don't want to solve it. Yeah, that's why. Yeah.
All right, anything else?
So I have a question on the slide on PUB, the pessimism by betting on unbounded coin.
Yeah.
So there was a part where it's sort of like you find V hat.
Yeah.
Yeah. So my question is, how exactly did you solve for V hat?
Yeah. So you use bisection.
Okay. Because
It's a strictly it's non-increasing function. So.
Is there any case that like it's difficult to find V hat like some?
No, we can give a solid theorem about complexity. Yeah.
Okay.
Yes. Oh, good question. I've thought about it, and it's not trivial. Yeah.
All right, cool.
Yeah.
Thank you very much,
Thank you.
Kwang. Thanks, everybody. What's your name? All right, okay. And next one, we got Raymond, who is, I presume, going to be talking about bandits.
Maybe I can start with the first slide. So I'm going to present our joint work. I am going to present our joint work with Eddy Adigi and Richard Combe from Central Supélec on linear bandits, on ellipsoids. Or maybe not, I won't present. See ya. So sorry about that. You have the title. Linear bandit and ellipsoid with Eddie Adigi and Richard Combe. So first, we are going to agree on what we mean by linear bandit and ellipsoid. And then I'm going to show that why we started to work on this simple yet nice problem. And then I'm going to show the result, the main result of our paper. So linear bandit and ellipsoid. So at each time t, you are going to select a decision belonging to an ellipsoid, centered in C and defined by a symmetric positive definite matrix A. And then what you're going to do, you're going to observe the reward, which will be the scalar product of your action with the parameter theta that you don't know, plus some sub-Gaussian noise of variance proxy sigma squared. And the goal, in our case, is to minimize the average cumulative reward, which is the difference between an oracle that knows theta and what you are going to do to try to estimate theta while minimizing this regret. So why did we decide to work on this paper? Because in the beginning we noticed that if the action set is a unit ball, and if the norm of theta is known, you can do exploration for d square root of t over norm of theta round on the canonical basis. And then you are going to estimate from this experiment your theta hat, and then you're going to commit on this decision. And you can observe that if you do this exploring for d square root of t over norm of theta, you have that the regret during this exploration is upper bounded by 2d square root of t. And at that time, the 2d square root of t, the d square root of t was the lower bound for linear bandits in general. So first question, is it really the lower bound when you know the norm of theta? Or you know an approximation of the norm of theta, and can we do better when you know this norm? And is it possible to estimate this norm quickly enough so that you don't increase the final regret? So from the literature side, there was some algorithm that provide upper bounds depending on this theta of norm of theta plus 1 over norm of theta d square root of t. And there was also an optimistic algorithm that have some maybe hidden dependency on the norm of theta and needed an upper bound on the norm of theta so that you have a regret guarantee and so that you can construct confidence interval for your estimate of theta. So here it's scaled linearly and inversionally linearly in theta, and here it's scaled linearly in theta, but you take out the square root of d. You earn the sigma square root of d with the term growing in theta. And on the lower bound side, there was some work from previous work that said that for any algorithm pi, there exists a theta tilde such that the regret is d square root of t. However, those hard instance parameters were usually around the origin of so that the norm is actually very small, and you know that for when you have a very small norm of the order d over square root of t, any algorithm will achieve 2d square root of t. You can do you can randomly act and you have nice regret. There was also another work that said that there exists a theta belonging to, so that the norm belongs to this range so that the regret is at least d square root of t. So can we do better if we know a bound on the norm? And where are those hard, all the linear bandit problem hard problem are concentrated in the center, or is there a lot of hard linear bandit problem everywhere? How to characterize and how to solve them. So before, we had minimax lower bound. So it said that for any algorithm, 1, 2, or 3, there exists a theta such that the regret of your algorithm will touch the upper line. Which doesn't say that if you know an upper bound of theta, maybe you can design algorithms that have very, very low regret, maybe. And we show that, and we want to compare that to the locally minimax lower bound that said that around each theta, you can have a small, you can take a small ball around theta and find a very hard problem such that each algorithm must touch the lower bound at least once around this theta for a fixed theta. So in the theorem form, it goes like this. So for any b, for any t, and for any algorithm, if you give yourself a theta of norm b, you can find another theta prime that is close to b such that the regret is big enough. And b is and in the order sigma d square root of t over 16. So what does it tells us for the linear bandit problem? It tells us that we have this lower bound that is everywhere, d sigma square root of t, and all your algorithm must touch at least once and go over this line for each each balls that you fix around the theta. Your algorithm must go over this, and it also means that the algorithm 3 does not exist, and maybe the proof is wrong or something. So you can. So here, if someone show not going to have this performance under the and for all theta under this sigma square root of t, the algorithm does not exist. So in what consists our algorithm? So first, we are going to estimate the norm of theta, find a lower bound and upper bound on theta. And then we are going to explore on the canonical basis for this amount of time, the sigma square root of t over beta b. And then we are going to commit to the best action so far, to the best action when you have the estimator theta hat. So how fast can we estimate the norm of theta? Quite fast, believe me, even if the formula is complex. But you can trust me that the probability of error times t times the norm of A is small relative to sigma d square root of t, and that the number of samples that you need to estimate the norm, the expected number of warm-up round, is small when you multiply it by the norm of theta. And then what you do is you commit, you do forced exploration for NE round based on based on the estimate that you have. And for that, you have that the average, the error of your estimator after NE round of forced exploration is less than this quantity. And you know that, and believe me also, that this quantity, when NE is of this range here, is small when you multiply it by t. So when you add up all those terms, you have that the upper bound of the regret is less than sigma d square root of t plus d norm of A plus minimum with t and norm of A. Because if you have very, very small norm in front of t, in front of sigma, in front of everything, the regret will be small nonetheless. So then I have some small experiments. So we try to plot the regret as a function of the dimension for different algorithms, from optimistic one, compared optimistic algorithm to this explore and commit strategy. And you see that it's more or less the same range. and it's maybe even better when you look at the dimension. And also, because of the bilinear optimization, it was hard to make an optimistic algorithm work in high dimension. So we stop at small dimension for optimistic algorithm. And then we do that for the norm to see that the norm does not impact that much the regret. And so for small norm, you have very small regret. For norm that are small but not too small, you have that our algorithm is a bit worse than an optimistic one, but for a big norm, it is better. So thank you for your attention. You have the paper here, you have the code here, and you have me here because I'm looking for a postdoc starting from March 2026, and I'm going to update my website because, yeah.
We have time for one question.
Thank you for the talk. Did you also plug in your estimation of the norm of theta in the optimistic algorithm, or did you run them with
I run them with a fixed parameter lambda, assumed to be greater than the norm of theta, but we can also do that for optimistic algorithm. Try to estimate the norm and then plug the estimate of the norm.
Yeah, I guess you could do your estimate part in front
Yes.
of any algorithm that requires an upper bound on theta, and,
Yes,
and you
that-
would
that-
get guarantees, like the same regret or...
Yes, that's true. But there's also optimistic algorithm that do not need an upper bound on the norm of theta now.
Okay,
There's work on that too.
thank you.
Squared in the number of exploration rounds?
Uh,
Because you said that, well, if the norm of theta is small, then you don't have big regret, but there's still some, factors
wait.
that can be large.
If you do the analysis, it's a bit technical when you add up the sum, but you can show that when you add up the sum, it's never bigger than d square root of t. It's just some tricks with bounding functions, but it's
Okay, so like small
it does
theta
not
cannot hurt
this
you.
thing does not explode because it's always upper bounded by t norm of a, the regret.
All right, cool. Thank you very much. Thank you. Right, and I think we have one more talk. Oh, okay. Look at the efficiency. Right, so the last talk is by Chava. You have like -1 minute to speak. Let's try to make it work.
Thanks, Gerge. That's very kind. Okay, so in this talk, I'm subbing Alireza, who unfortunately couldn't be here. He really wanted to come, but doesn't have a visa, obviously. So this is joint work with Alireza, my student, Tor, and myself. And the work explores Thomson sampling for bandit convex optimization, more specifically in the Bayesian setup. I guess you press this? Okay, yeah, green button. And you can go back. I see. Okay, cool. So the goal is to understand Thomson sampling and how it works in this bandit convex optimization. Bandit convex optimization is everyone's favorite, right? We're going to study this only in the Bayesian setting and only in some specific cases. And we are going to have, okay, so that's for the positive results. For the negative results, we do have some bad news for the fans of Thomson sampling. So we show that Thomson sampling suffers exponentially in the dimension regret for general convex losses in d-dimensional problems. So you probably not advised to use that algorithm for that setting without modifications. And also on the negative side, we show that the usual proof techniques that are using these information ratio tricks are not going to get you too far. That's in a nutshell, but mostly I'm going to focus on the positive parts. The negative results, they're interesting constructions if time permits. We will see. We can go into those, but yeah, it's usual lower bounds. All right, so for the positive side, so let's take a look at the problem setup. Standard thing, you have a convex body in the d-dimensional space, and you have a set of convex functions from this convex set to 0, 1. So we are only considering bounded convex functions. And we're Bayesian, so we have a prior over this set of functions. In round T, the learner plays some action from this convex body, and it observes a scalar loss, which we assume to be Bernoulli for the sake of simplicity. Obviously, you can extend this to the Chirac case. But the Bernoulli case is kind of like just very neat for analysis. So that's why we do it. And of course, the loss is connected to the actions that you have chosen in previous losses by that its conditional expectation given the history, and this unknown function f is exactly given by the value of f evaluated at the last action that you have chosen. And f is this function from this set. And we're going to assume that this is a Bayesian setting, so f is sampled from this prior psi. A learner just maps histories and the prior to k, and the Bayesian regret is, as defined here, you're taking expectation over everything, including f. Clear? Very standard. So Thomson sampling, everyone loves this algorithm, super simple to write. In every time step, given the observations, you know that you have a Bernoulli noise, so you can calculate the posterior, and you sample a function from the posterior, and given the function from the posterior, you find its minimizer, and you're going to play that. It's very simple, very cute, very elegant. And the question is whether this is a good algorithm for this bandit convex optimization problem. Good. All right, so the technical upper bounds look as follows. We're going to study two function sets. The first function set is just one-dimensional. Basically, both of them are kind of just one-dimensional, but like the second one is a little bit more complicated. It's kind of like, anyways. So the first is one-dimensional, truly one-dimensional. So you have basically an interval of the real line, and the functions are going to be one Lipschitz and bounded convex. The corresponding function class is BL, FBL, bounded in Lipschitz. The other function class is bounded Lipschitz, ridge, and monotone. So that's, it looks like that. So the value of f at a point x is the inner product of x with an unknown parameter theta, and then you apply a ridge function to it. And you assume that the ridge function, this L function, is monotone, and this whole thing is convex. One Lipschitz is bounded. And the two main positive results are that in one dimension, Thomson sampling is not so horrible. It achieves square root and regret bound. So that's actually pretty good. And in the other setting, you get d to the 2.5 for Thomson sampling, which is somewhat greater than, as usual, than the best possible upper bound so far. But it's still like a modest scaling with a dimension. At least you don't blow off as a dimension. All right, so these are the upper bounds. And how do we get there? We use the more or less standard information ratio based analysis. There needs to be a little generalization of this. So notice that here, rather than, usually you just like compare, okay, so what are these quantities? All right, okay, I only have 5 minutes. So then all it is so that like I'm gonna give you like, I don't know, an hour lecture, so I have plenty of slides. Anyways, so this information ratio, maybe I just explain the information ratio and then we'll have to call it a day because time's flying. So how does this work? You have this distribution psi. Distribution psi represents a posterior over the space of functions. You sample from this distribution psi 2 functions, f1 and f2, and you compute 2 quantities. One is kind of a regret gap, and the other is kind of like an information quantity. So the first quantity there, this still doesn't point, is that of psi. So that of psi compares, you know, like you first calculate the expected function, and there you have a bunch of difficulties in the rich case because that's like the set of rich functions is not convex, so there you might be leaving your function space that you love. Anyways, you do that, and you compare the value that you would get at the optimum of of one of the sampled functions with the random optimum that you would get otherwise. So that's the gap. And the other, the information quantity compares the values similarly calculated at f1 and f bar, but at the other optimizer, and then you're squaring it. So it's kind of like a variance type of quantity. It measures like how much information you're going to gain if you choose this psi, and the other is related to the regret. And classically, you want to say that you can bound, like nice things are going to happen if you can bound the gap in terms of the square root of the information up to a constant factor. It turns out that that wouldn't quite work for our case. We have to add this little constant or bias factor. There is some price to be paid for that in the regret analysis, but it's not too horrible. And you can control these things, and then that will make the analysis work. All right, so with these definitions out of the way, the very high-level outline of the proof is as follows. For these 2 specific function classes, following techniques from previous works, given this generalized information ratio definition, you can prove that the Bayesian regret of Thomson sampling is upper bounded as follows. And now what remains is to show that this alpha and beta, you can find appropriate alpha and beta such that you have a nice regret bond. So the question is, how do you do that? For that, we are introducing this partitioning idea where you're given an f tilde function. So think about the f tilde function of the f bar from the previous slide. So it's like the expected value of a function randomly sampled from posterior. And given that, you introduce a partitioning such that you postulate that this inequality holds, which looks a little bit complicated, but on the left-hand side, you still have gap-like quantities. On the right-hand side, you kind of have the variance type of quantities. And you can see this is kind of like a discretization of what was happening before. And you just want to establish that there is a finite k and m such that this holds. This inequality holds, because if that holds, then you will have this general result that this alpha and like k squared m beta is a generalized information ratio. All right, time's up. So then you do this, you do all of that, and then, okay, so this is super important to explain every detail of this slide. So k can be chosen to be 4 in the one-dimensional case, and that's like a beautiful geometric result, like not too hard to prove, but it requires some effort. And this is how it goes, like you draw some lines, and then things happen, and then things are impossible, you change things, and you figure out that you cannot push this more than 4. It's proved by contradiction. And then you can have the lower bounds. Paper on one slide. We have some positive results, negative results. Thanks. If you want to chat more, I'm around. Thank you.
maybe one question.
Can you maybe just give a quick intuition of why there is this limitations of using information ratio-based tricks for lower bounds?
What? So what?
The second negative results.
Oh, the second one.
The one about
Yeah,
neg.
so this is the figure for that. It's you construct these spheres and then this lower bounding functions and then you can just like stuff there.
Okay. We can talk about it later. Maybe. Thanks.
So why is this monotonicity assumption important?
Well, it was super important in this geometric part of the proof that monotonicity is there. We couldn't remove it. Yeah.
And can you do something like the squared loss or something, or can you go a little bit beyond?
Maybe if you have some really specific set then, or specific function, then yes, but in general we couldn't remove the monotonicity. Pretty bothersome.
All right, cool. Thank you. It's time for coffee.